In this video, we're going to go over curve sketching. Basically, that means we are going to graph some functions. As we graph the functions, you're going to see I use the same things all the time. I'm going to want to know the domain, x and y intercepts, asymptotes, any local max or local min, the increasing decreasing intervals, inflection points, concavity, and lastly, we will graph. I want you to pay attention to the fact that I don't always do this in order. So I'm going to go through and get the relevant information that I need and then fill in the blanks. What I want us to do is make good choices. I don't want us to spend a ton of time doing all of these graphs. So I think the information we have kind of tells us more information sometimes. And I'll just show you what that means as we go. So we're going to start with f of x is x plus 2 over x plus 7. The domain would be any x not equal to negative 7. What I'm looking for is the denominator equal to 0. So what I want to say here is x cannot be negative 7. So maybe make a note to yourself of how do I find the domain? I look at the denominator, I set it equal to 0. The x-intercept comes from where the function f of x is equal to 0. So this time I'm taking the numerator and making that equal to 0, which says x is equal to negative 2. For emphasis, I'm going to write this as a point, negative 2, 0. I want you to pay attention to the difference between how I write an intercept and how I write an asymptote. So just leaving it as x equals negative 2 kind of looks like a line, so I want to write it as a point. The y-intercept says plug in 0. So this is f of 0. That's going to give me 2 over 7. Again, for emphasis, I'm going to write that as a point, 2 over 7. Asymptotes. Okay, this one's going to take a little more time, so let's go over here and say we have 3 kinds of asymptotes to consider. Vertical asymptotes, these come from the denominator being equal to 0. So kind of like we started with looking at the domain, except this time, when I make x plus 7 equal to 0, I leave it as x equals negative 7. Watch the slight difference between asymptote is a line, x equals negative 7, versus domain, I tell you x can't be negative 7. So the equal sign with a slash through it for domain and the equal sign for asymptote. Horizontal asymptote, we have those 3 rules. This particular time I have x on top, x on bottom, they're the same power. My asymptote would be the coefficients 1 over 1. So see how I can put a 1 in front of the x, a 1 in front of the x, 1 over 1 is 1. So I have y equals 1 as my horizontal. Having a horizontal says I do not have an oblique, so I'm going to write the word none there just to emphasize that I don't have an asymptote. So let's start with a blank page to start looking at derivatives. So start with first derivative. I have to use the quotient rule. So quotient rule says low, x plus 7, d high is 1, minus high, x plus 2, d low is 1, all over the denominator squared. I can just drop the 1, so it's the same as distributing them. I have x plus 7. Pay attention to it's minus x minus 2 from the negative sign in front of the x plus 2. I have x plus 7 squared. The x's cancel. In the numerator, you have 5 over x plus 7 squared. 5 is positive. X plus 7 is positive. You can tell from this derivative, without doing any more work, that this first derivative is always greater than 0. Now, I do have this time where x is negative 7 and the first derivative doesn't exist. That's okay. But what I want to be thinking about is everywhere else, 5 is positive, square is positive, the derivative is positive. Positive means it's increasing. So I immediately know this is increasing from negative infinity to negative 7, and then from negative 7 to infinity. I split it at this partition number, which would be negative 7. There's not a critical number for this one. 5 is never going to be 0, so I'm not going to have a max or a min in this one. That's also important to say, so let's just say right here, no max, no min. That'll save us time later. So already we know the increasing, decreasing, we know the local extrema, we know there aren't any. Well, let's kind of piece this together and look at what we think that looks like. So what did we say earlier? We said we had a vertical asymptote at negative 7 we had a horizontal asymptote at y equals 1. We had an x-intercept at -2, and we had a y-intercept at 2/7. If I follow along right now and make this only increasing, I'm increasing up along the asymptote. I go over to the x-intercept, hit the y-intercept, and this continue along the y equals 1 horizontal asymptote. Now that was the right side of x equals -7. On the left part of x equals -7, there are two parts it could be. So I could have this green curve that's going up. So I'm following along the y equals 1 and up through x equals -7. Or maybe it's this blue part that comes along the y equals 1 and down the x equals -7. So what we have to decide is which one of these is the graph supposed to be. Well, the clue is it's always increasing. When you look at the blue curve is going down. The green curve is going up. So the only thing that could be increasing would be the green. Right. We can also save the time here to say there's not an inflection point. There's not a point where it changes concavity, but we do have concavity. The green part of the graph we drew, which goes from -infinity until -7, is concave up. And then the original part that we drew that goes from -7 to infinity is concave down. Now watch what I didn't do. I didn't do a first derivative test. I didn't do a second derivative test. I took the first derivative. I saw that I couldn't set it equal to 0. I saw that it's always increasing. Then I took the algebra piece of our intercepts and asymptotes, put that on the graph, and I was able to pull out the rest of the information. This saves you time, so I highly encourage you to try to do the math this way. Let's try another case and see if we can do the same kind of thing. So this time I have f of x is x over x minus 2 squared. Again, first thing I asked is, what is the domain? So the domain is everything except x equals 2. So remember, I'm going to put a not equal to say I can't have the value of 2 because it would make the denominator 0. The x-intercept is, where is this function equal to 0? Well, you look at the numerator and you take the x and you set it equal to 0 and you get 0. So this 0, 0 is the x-intercept. Well, 0, 0 is the origin, and anytime you get an x-intercept of the origin, you immediately have that the y-intercept is the origin. You could check it. You could plug in f of 0. You would get 0 over 0 minus 2 squared. You still get 0. Asymptotes. Remember, we have to check all three. So I start with x minus 2 squared equals 0 to find my vertical asymptote. The square doesn't really matter. You could take the square to both sides and you would still get x minus 2 equals 0. So I have x equals 2. So there's my vertical asymptote. Horizontal asymptote. The degree in the denominator is 2. Even if I don't multiply it out, the power is 2. Power on top is 1. So the bottom being bigger says the horizontal asymptote is 0, which means the oblique is none. To find the derivative of rational functions, we're almost always using the quotient rule. This time, the quotient rule will also involve a chain rule from the 2 from the x minus 2 squared. So we're going to start low, x minus 2 squared. D high is 1, minus high, x, d low. The 2 comes down. I have x minus 2, now to the power 1. Derivative of x minus 2 is 1. I'm going to put that at the back. And then all over the bottom, x minus 2, now to the power 4 because we're doing squared, squared. Okay. I notice I have x minus 2 in the first term, in the second term, and in the denominator. So since it's common to all three places, I can factor out 1 x minus 2. So I'm going to take 1 from here, leaves me at the power 1. I'm going to take this term completely out, and in the bottom now I have power 3. This simplifies to x minus 2. And then the right side I had minus x times 2 times 1, so that's minus 2x over x minus 2 cubed. X minus 2x simplifies to negative x minus 2 over x minus 2 cubed. I need to set this equal to 0. When you set a fraction equal to 0, you're looking at the numerator. So let's take negative x minus 2 equals 0. This is negative x equals 2. X equals negative 2. This is our critical number. So we have a potential, max or min. Let's look at what we have so far. So far we said we have a vertical asymptote at x equals 2. We have a horizontal asymptote at y equals 0. And we have an x and y intercept at the origin. We have a critical number at x equals negative 2. To find the y coordinate, I'm going to plug negative 2 into the original function. F of negative 2 is negative 2 over parentheses negative 2 minus 2 squared. In the numerator, I have negative 2. In the denominator, negative 2 minus 2 is negative 4. Negative 4 squared is positive 16. So this gives me negative 1 over 8. So over negative 2, I'm just going to be right under the x-axis at negative 1 over 8. So we need to do a little bit more work because we can't really tell what's going on here yet. We need to find out if the function's increasing, decreasing. We need to look at concavity. So let's go ahead and take the second derivative. Okay, second derivative is going to require the quotient rule again. So we're going to have low, x minus 2 cubed. D high is negative 1 minus high. Put in parentheses negative x minus 2 because I don't want you to lose any of those negatives. And then d low. The 3 comes down. We write x minus 2 squared. And derivative of x minus 2 is 1. This is all over the denominator squared, so we had x minus 2 cubed. When we raise that again squared, that's going to give us power 6. Just like last time, we have this x minus 2 multiple times. I have a 2, I have a 3, and I have a 6. That means you can take 2 out. So I'm going to take 2 from here, I'm going to take 2 from here, and that's going to leave me with 4 in the denominator. Let's see what we can do to make this look better. Our second derivative. X minus 2 times negative 1 is negative x plus 2. Then on the right side, I have a negative, I have negative x minus 2, and I have 3. I'm going to think about multiplying everything times negative 3. So negative 3 times negative x is positive 3x. Negative 3 times negative 2 is positive 6. And this is all over x minus 2 to the 4th. 3x minus x gives me 2x. 2 plus 6 gives me positive 8. And that's over x minus 2 to the 4th. We need to look at where is 2x plus 8 equals to 0. 2x plus 8 equals 0 when 2x is negative 8, which says when x is negative 4. This is our inflection point. To find the y-coordinate, we need to find f of negative 4. We have negative 4 over negative 4 minus 2 squared. We have negative 4 on top. Negative 4 minus 2 is negative 6. Negative 6 squared is positive 36. Negative 4 over 36 is negative 1 over 9. If we go back and look at our graph, we had a critical number at negative 2, negative 1 over 8. Now we have an inflection point at negative 4, negative 1 over 9. Negative 1 over 8 is negative 0.125. Negative 1 over 9 is negative 0.111. So negative 1 over 9 is slightly closer to the x-axis. Let's take our critical number, negative 2, negative 1 over 8, and let's connect it to the 0, 0 we have as our x and y intercept. Think about what it means to be a critical number. It says that's where things are going to change from increasing to decreasing or decreasing to increasing. I was increasing from negative 2 to the x equals 0. I have to stay increasing. I don't have another critical number. So as I go from this point of negative 2 over to the 0, 0, increase, which means I'm going to go up along the vertical asymptote at x equals 2. Look at the concavity. The concavity, we can see, is concave up, and it will continue to be concave up until it gets to the inflection point, which was at negative 4. So if I draw this part, it needs to also look concave up. So from negative 4 over to negative 2 and continuing through the 0, it should look concave up. It's going to switch concavity at the negative 4, since it's going to be concave down. Now I have to be really careful at this concave down because we have a horizontal asymptote that it's supposed to follow. So as it goes concave down, it's going to follow along the x-axis but stay under it. Our only x-intercept was at 0, 0, so this is going to be just under that when I look at it. So it was concave down until it got to -4. It's concave up from -4 to +2. We have this point. Now look, it went down and then it went up. This makes this a local min. We still have the right side of the graph to figure out, but we do have some help. We know there's no critical point, and we know that there's not going to be an inflection point. So whatever happens is going to happen for the entirety of the graph. So what we could do is pick a number on the right of the vertical asymptote. So the asymptote is at 2. Why don't we try something like f of 3? F of 3 is going to be 3 over 3 minus 2 squared. We get 3 over 1, which is 3. So what are we looking for? We're looking at position. We're trying to say, where's the function going to be? Is it going to be above the x-axis or below the x-axis? Since we found out when we put in 3 that we get out 3, we know that the graph's going to be above the x-axis. It's going to be following down the vertical asymptote. It's going to hit this point, and it's going to continue to go down. There is no maximum, there is no minimum. I can also tell you concavity. This is concave up everywhere from 2 to infinity. Let's try to wrap that up and summarize. So I put on that we have a critical number at -2, -1/8, that's our local min, and then we had our inflection point at -4, -1/9. Our function was decreasing from -infinity until -2, then it was increasing from -2 to +2, where we had our vertical asymptote. Then from 2 to infinity, it was decreasing again. For concavity, it was concave down from -infinity until it got to -4. It switches and becomes concave up from -4 until it gets to the asymptote at 2. It's also concave up from 2 to infinity. This is a graph where looking at Desmos will be a good validation. Like we'll feel like, yeah, we can see the up down, but maybe we wouldn't have seen the inflection point. We wouldn't have seen the local minimum by looking at Desmos. So it's important that we use the graphing utilities as a supplement, but we don't rely on them. So let's take a quick look at that. Remember, our function was f of x is equal to x divided by parentheses x minus 2 squared. So when we look, you can see here at -2, -0.125, that we have a minimum. I think it's pretty hard to see the inflection point, but let's put it on there. Let's do -4, f of -4. So now I can click on it, and it will tell you it's -0.111, which was our -1/9. It's pretty hard to see the concave down. If you really want to see the concave up, concave down switching here, we would need to zoom in a lot. So I'm going to hit the settings. And what I need to change is the y, and I need it to be really small. So maybe it's going to go from -0.2 to 0. Now you can really zoom in and see what's happening, and you can see these points that we talked about. So here's this -4, and zooming out, you can see the concave down. And I can put in the critical point, -2, f of -2, so you can see this minimum. So sometimes it's pretty tricky. You have to know what you're looking for when you're trying to find the inflection point, so you really have to rely on the calculus to get you there. The graphing technology is a nice assist, but it won't show you everything that you want to see.